geometry, we can write that EI is going to be given by that equation there, where the x cap cos theta I minus z cap sin theta I is, you can recall this to be the resolution or resolving of ni cap, which is the unit vector in the direction of propagation, into the x and z coordinate. And therefore, this other one is just follows from the same previous discussion we had yesterday. It's the propagation factor, so to speak. So the H field, the H itself, the incident magnetic field intensity, is therefore going to be given by the direction vector cross the electric field intensity and divided by the intrinsic impedance of the medium through which the wave is propagating. And once we do this, we can see that we'll just be left with a y, okay, positive y direction for the HI, just like the figure shows. But if we were to interchange, we would get a minus, so to speak. And ER, or the reflected electric field intensity, is also given by the same kind of value like we did before, and HR given by that. So what you need to carry out is that you remember always that ER for a TEM wave, ER or the electric field intensity and the magnetic field intensity are related by equations of that nature. That is the direction vector cross the electric field intensity vector and divided by the wave impedance. If you are to be given the H, all you have to remember is that you can multiply that by whatever, by the impedance, and then take the cross product with respect to the direction vector and then expand. And you'll find that you'll always get the one from the other for TEM waves, so to speak. So like before, we'll assume that the conductivity of medium 2 is large, okay, and is sufficiently large such that the electric field intensity vanishes inside the conductor. So the continuity of the tangential component of the total electric field intensity at the boundary will then require that the EI, the x component of the incident electric field intensity and the reflected field intensity must go to 0. So because the x component of those fields are the ones which are parallel to the interface, and therefore when we do that, we can add them together and we see that the x component will have that kind of direction. And we, like we said before, for this to be the case, then the phase propagation or the phase factors that we have here must always be the same for it to hold for all x at the boundary. Okay? So again, we see that for this case, theta r is equal to theta I, and therefore an ERO must therefore be equal to the minus of EIO to make this equation equal to 0. And this, we record, is again the Snell's law of reflection. And therefore, the total field in medium 1 is given by the superposition of the incident and the reflected wave components. And we see that we have an x component pointing in the minus x direction and our z component pointing in the minus z component. What you need to remember is that the x component has a j, that is, it's at 90 degrees, okay, out of phase, time phase, with the z component. And look at the variation of the amplitude is going to be given by the cosine of theta I and the sine of K1Z cos theta I. Okay, that is the amplitude variation. For the Z component, we see that the amplitude variation is multiplied by a sine and cosine of K1Z cos theta I as well. So the H field obtained from the cross product of the unit vector with, in the direction of propagation by that and divided by eta 1 will be given by that value. And we see again it has an amplitude that varies as a cosine of K1Z cos theta I away from the interface. Therefore, we can note the following. In the z direction, that is in the direction normal to the interface, E1x and H1y, okay, have a standing wave distribution according to the sign of K1z cos theta I for Ex and cos K1z cos theta I for H1y respectively. They are in quadrature time phase because we have seen that the H field does not have a J, while the X component of E1 has a J of multiplying it, that is meaning that it's out of phase by 90 degrees. In the X direction, that is in the parallel direction to the interface, we have a Z component, the Z component of E1 and H1y will correspond to a traveling wave or a propagating wave that is propagating in the positive zx direction and with a phase factor given by exponent of k1x sine theta I and a phase velocity v1x equal to v1 by sine theta I, where v1 is just simply omega by k1. In the literature, k1 sine theta I would be written as kx, okay, but I'm just keeping the K1 intact to show the unbounded media kind of, equation, so to speak, so that we don't have too many variables or constants to deal with. Now, these two components, E1Z and H1Y, are in time phase. There's no J operator in any of them, and in spatial quadrature phase, because E1 is pointing in the y direction and H1 is pointing in the y direction and E1Z is pointing in the z direction, and therefore they must be facing in different directions in space. So the propagating wave is non-uniform again because the amplitude is corrected by that equation there, where Z is measured from the interface. So for the standing wave, there are planes of amplitude, maxima, and nulls of Ex along Z at given values of K1 Zm sine theta I equal to the minus of twice m plus 1 pi by 2. Okay? This will be because we want to make sure that always sine theta I is always equal to whatever. That is where the values of the equations K cosine of K1Z cos theta I is equal to 90 degrees will give us the value, so to speak. Of course, I think this is what I'm talking about. Yeah, we have a sign. So we want this value to go to 0 for that particular case. Or to go to a maximum, this must be 90 degrees rather. And the minimum points where the Ex goes to 0 is the case where that argument is equal to 0, is equal to pi, or multiple integer multiples of pi, and we get the value that K1 Zm sine theta I is equal to minus 2m pi for m equal to 0, 1, 2, and so forth. Okay? So remember what we said about the negative sign here is because we are assuming that Zm is measured from in the negative Z direction. In the literature, you may find them changing that to something like Zm prime and so forth. Thus, we can insert a conducting plane at any plane where the electric field is 0, and we won't change the distribution of the electric field intensity between the two planes. That is the plane at the interface and the plane that we are introducing. And therefore, when it's placed at those values of Zm, then will not affect the distribution between the conducting plane. A transverse magnetic TM wave, that is where H1 of X is equal to 0, would thus propagate in the X direction between the two conducting planes. Again, that is what we call a parallel plate waveguide. The spatial distribution of E1 and H1 for oblique incident represents interference patterns. And if the incident wave is confined to a narrow beam, the reflected wave is going to be a narrow beam as well, and will be propagating in a different direction, and therefore we can expect to have, a communication whatever system whereby we don't have any interference between the two waves, so to speak. So if you have looked out, you have seen that the Safaricom base stations, they have dishes, satellite dishes, pointing in different directions. What happens is that if you are not using, they are using radio waves, so a radio wave will be intercepted by the antenna of the dish by reflecting through, and then it will be amplified and then sent out again. But we expect that the amplification and retransmission will be without distortion because of this idea that the incident wave will be confined in a narrow beam, and therefore the interference pattern that is produced by the distribution, spatial distribution of E1 and H1 will be confined only very close to the conducting plane, which is the dish surface that is behind the antenna. Now, we can look at this. Now we look at normal incidence where we have a plane surface between two dielectric media, which we are calling now a dielectric-dielectric interface. Remember, although I've treated these things separately, we could always use one of them and then start playing around with the constitutive parameters of the second medium. But I thought it was more prudent for us to look at this in, in steps, media per media, so that we can appreciate what it is we are doing. And therefore, the following discussion will be exactly the same as the other discussion we had, only that now sigma for the two interfaces is going to be 0, so to speak. But remember, we can always use a sigma, and then we can use one treatment and make the sigma 0 for the appropriate case that we are dealing with for that particular time. So this, therefore, I'll go through very quickly and say the following. So we are going to consider a linearly polarized wave. By linear polarization, remember, we are just saying that E points in one direction as time evolves at a given point in space where we are observing the wave. So the media are assumed to be lossless, and therefore there are no free charges in any of the media. And therefore we can see that the incident wave has been assumed to be polarized in the x direction. This is by assumption. You can polarize it in any direction for this normal incident, and nothing will change. And HI is polarized in the y direction, and therefore NI is our direction, the incident direction of propagation, and the NR is the direction of of propagation of the reflected wave. And we see that we expect as well a transmitted wave that will not change from that of the EI. They'll have almost the same kind of direction with the quantities as shown in the diagram. So the media are characterized by sigma equal to 0, and we have the constitutive parameters mu1 epsilon 1 and mu2 epsilon 2 respectively. So reflections at interfaces is more like an accountant that is trying to do bookkeeping, where we are trying to get, to keep the two sides balanced. And that's the end of all we need to do. Once you have written down the equations, or the equations of the electric fields and the magnetic fields, the rest is just accountancy, so to speak, using the boundary conditions that we have already met. So in medium 1, therefore, we have the incident parameters, that is E1, EI, and HI, as given by this equation. We also have the reflected wave with ER given by that and HR given by that. The equations themselves, we are going to, since we are dealing with plane waves, remember we shall just have to use these values here. If we are using other types of waves, then this may be different and the equations become a little bit more weird. But since we are dealing only, we want only to know about how the wave behaves at the interface, then we use the simplest expression of the waves or the wave fields as possible. Okay? But most times we find people trying to use plane or whatever circular or cylindrical interfaces, and that one is much more difficult to analyze. And that's why we are using a plane interface, okay, so that we can keep this discussion simple. What we notice is that the unit vectors or the direction vectors are given as follows. Ni is in the same direction as z cap, nr is in this opposite direction as z cap. So in medium 2 as well, we have the following transmission, the transmitted fields in the form of that value. Usually when you are given this in a problem to solve, you will be given, you will be awarded or credited for writing down the equations that you are going to be dealing with. What you need to notice is that since we are dealing with medium 2, it has a different wave number, K2, where K2 is, of course, omega root mu 2 epsilon 2, just like we have seen for the unbounded medium. And again, the direction vector for the transmitted wave is also in the direction of z cap. So the continuity of the tangential component of the total fields at the interface will therefore require that the incident electric field intensity plus the reflected electric field intensity must be equal to the transmitted electric field intensity. And it's not for every point of Z, but just at the interface. That's all we require, just at the interface where we are saying Z is equal to 0. The magnetic field intensity as well will satisfy that equation. And therefore, once we use the definition for EI, HI that we obtained before, and HR, okay, we can see that EIO plus ERO is equal to ETO, and EI0 by eta 1 minus ER0 by eta 1 is equal to ET0 by eta 2. So this represents that equation for electromagnetic field, and that equation represents that. So we can therefore write that ER0 is going to be given by the component eta 1 or eta 2 minus eta 1 over eta 2 plus eta 1 multiplied by the value of EI0. If we define this expression for the intrinsic impedances as gamma and call it a reflection coefficient for the interface, then you can see that ER0 is related to EI0 as gamma EI0. And the transmitted amplitude, wave amplitude, is going to be given by twice eta 2 over eta 1 plus eta 1 EI0, which is equal to tau EI0, where tau is now the transmission coefficient. So, by definition, that is given there for you. And we can recall that these are the same values that you had when you are dealing with transmission lines in the third year of ECT, where this would be the, say, for example, the load terminating a transmission line of characteristic impedance eta 1. Now, we note the following. Gamma can be either positive or negative, but but tau, or the transmission coefficient, will always be greater than 0. If we added 1 to unity to gamma, or the reflection coefficient, it will always be equal to the transmission coefficient. So if medium 2 was a good conductor, that's what we were talking about, then eta 2 would be very close to 0. It would be eta m that we found before, and gamma will go to -1 and tau will go to 0. Okay? And ER0 will then be approximately minus EI0, and ET0 is approximately 0. This is what I was talking about, that we can just use a plain dielectric-dielectric interface to discover or to discuss the reflection and refraction properties of a wave at an interface, so to speak. Then use the appropriate parameters for the media to make deductions as to how the waves or the wave components are related to each other. Now, if the dielectric itself had loss, that is sigma, or the conductivity was non-zero, which means then it must be containing free charges in itself, then this would happen. The reflection back into the medium, okay, would be partial, because some of the transmission will go through, will penetrate, some of the field will penetrate the second medium, okay, and some of it will be reflected back, just like we have seen for the dielectric-dielectric, the lossless dielectric-dielectric interface. We have a transmitted wave that is non-zero and a reflected wave that is therefore partial, so to speak. And therefore, if we were to add those two values, we can do the following. We can write that the electric field intensity, as we saw it before, we can write it in two forms. We know the value of EI0, and we know that EI0 multiplied by gamma gives us ER0. And therefore, we can always take the EI0 out, and we have just the exponent of minus jk1z plus gamma exponent of plus jk1z. This shows a wave that is traveling in the minus z, in the positive minus z direction. And therefore, once we look at it this way, we can see that if I was to add a gamma, I multiply this one by gamma and subtract it, okay, I can always get a value for the transmitted and reflected wave component. And this is what we have done. So here, we have added gamma multiplied by exponent of minus jkz, and then we remember to remove it again, okay, which we remove it here. So we add it here, and we remove it here. And therefore, if we recall that 1 plus gamma is tau, then we can see that this equation reduces to x cap EI0 tau exponent of minus jk1z, and we see that this is a transmitted wave component into medium 2 plus, or a traveling wave, so to speak, not a transmitted wave. And this would be given as twice gamma sine k1z. And this, because we don't have, this one does not look like that. We see that this one is a standing wave pattern, so to speak. So this would be a propagating wave component, and that is a standing wave. And because of this component here, E1z will not have planes where the electric field vanishes like we had for good conductors, but it will have a minimum value rather than a zero, a null, so to speak, because of this traveling wave. Okay? So we can say that the total field in medium 1 therefore consists of a standing wave component with an amplitude of twice gamma EIO. And 2, it has a propagating wave component of amplitude tau EI0. This, remember, it has a 2 which has been left out typographically. It's a typographical error there. And because of the traveling wave component, Then E10 exhibits non-zero minima at fixed planes along the z-axis. And the locations of the planes of extremal, the extremal points of E1 can then be determined by rewriting the expression for E1 in the following way. We just write it again as before, but rather than adding the gamma E exponent of minus jk1z in there, all we do is to factorize or to factor out ei0 exponent of minus jk1z into 1 plus that. And because we are adding, what we are doing is that we are assuming that gamma is not exactly a real value, but it's a complex value, especially when we have a lossy material, and therefore we are giving it a phase angle. So we use the magnitude and phase expression, and we can see that we can always factor it out together as twice k1z plus theta gamma. That is the angle of the reflection coefficient. So for lossless media, we note that eta1 and eta2 are going to be real values. It's just the square root of mu1 by epsilon 1, mu2 by epsilon 2 square root for the second medium. And we remember that when the medium is lossy, mu1 and the mu's and the epsilons can be written as complex values, and therefore eta1 and eta2 will be complex impedances. But now, since the media are lossless, these ones are real whatever impedances. And therefore, because of that, because the reflection coefficient and the transmission coefficient are only functions of eta1 and eta2, then they themselves will also be real. Now, suppose we have that the transmission coefficient is greater than 0. Then it means that the angle of the reflection coefficient is going to be equal to 0, and therefore it means that eta2 is greater than eta1. In the expression for gamma, we saw that it was eta2 minus eta1 over eta2 plus eta1. And therefore, eta2 must be greater than eta1 for it to be positive, as we are assuming here. And therefore, this will give us a maximum value for the magnitude of E1z, okay, at the given point. And we can get it as Ui0 into 1 plus the modulus of gamma. And 2, the minimum value will be when we subtract the gamma from the from unity, and therefore we'll get a minimum value of Ei0 into 1 minus the modulus of gamma. Okay. So an electric field intensity maximum will then occur at a plane for which the 2k Zm is equal to minus 2n pi, because theta gamma is equal to 0, therefore it doesn't appear there. And we'll see that in this particular case, there will be a minimum value at the interface, or the maximum value will be at the interface, and then the rest will follow away at those at planes that satisfy that equation. Or in other words, you can say that Zm is going to be given by the minus of n pi by k1, which we see that is just going to be the minus of n k lambda 1 by 2, or half wavelength, okay, at intervals of half wavelengths away from the interface, we'll have a maximum in the electric field intensity. We don't need to belabor the point. The magnetic field intensity will be minimum at these locations as well. So the intensity minimum will occur at planes for which the 2k 1 Zm satisfies that equation. That is, it's an odd multiple, odd integer multiple of pi. That's where the value is going to be negative, because if we look at the expression for gamma, we can see that then that will have a minus. That is, if we were to look at this, let me go up a bit, and we were to look at it, in which case we have this one equal to 0, then twice k1z, it will be the cosine of an odd multiple of pi therefore making it negative, okay, and making therefore this one a smaller value at those equations that we have shown down below, and show it now again. Now, where did I go? This is where we are. And therefore, when we put in the values of k, you can see that this value here is just going to be given by lambda by 4, okay? And remember, the wavelength here is in relation to the unbounded medium 1, okay? The wavelength of the wave in the medium 1 at the operating frequency, okay? So, now if we look at the other case where gamma is less than 0, then theta can be taken to be equal to pi. And this means that eta 2 must be less than eta 1. And therefore we expect that the maximum will be where the gamma is going to be, you know, that value is going to be whatever 1 minus gamma, and the minimum is going to be 1 plus gamma there. So an intensity maximum will occur at the plane located where the intensity is a minimum for gamma greater than 0, that is at z equal to m, and an intensity minimum will occur at a plane located where the intensity maximum for gamma greater than 0, that is Zm. Okay, so the only difference is that it's an interchange of the two cases that we had before. That is, before we saw that this was the location for the electric field maximum for gamma greater than 0, not the amplitude, but the gamma greater than 0 itself. And this was the location for the minimum case in the other case there. So the ratio of the intensity maximum to the intensity minimum is defined as the standing wave ratio on that particular interface, and we give it the symbol S. And therefore, we can write that S is by definition given by E1Z max over E1Z min. And we see that it's just going to be given by 1 plus the modulus of gamma over 1 minus the modulus of gamma. Okay, this is in your transmission line theory, you called it the voltage standing wave ratio. And since the E1 is proportional to the voltage, then this can be also be seen to be the voltage standing wave ratio. If you are asked to get it using the magnetic field intensity, we see that it will be the opposite, it will be minus of this value here. And that's the one you call the current standing wave ratio. But since they are all the same, we usually just by convention just reduce and use the standing wave ratio as defined for voltages. So we can therefore get a value of gamma, of the modulus of gamma, in terms of the standing wave ratio in the following form, that gamma is equal to S minus 1 over S plus 1. If the reflection coefficient is equal to 0, it means that S is equal to 1, okay? And therefore we'll get this going to 0. And when the gamma is equal to 0, it means that there is no reflection at the interface and the wave goes through without reflection. And therefore you see the minimum value of S is going to be 0, so to speak. Okay? Now, suppose we have total reflection where gamma is equal to minus unity like we had before for the good conductor. Then we would see that the S would go to infinity, because 1 minus 1 of course is 0, and we will get it going to infinity. And therefore the range of S is very large. It's from 1 to a very large number, which is infinite number, so to speak. And therefore in engineering, we usually redefine this S and we specify it in terms of decibel scale, and we call it that we give the S in the dB scale as SdB equal to 20 times the logarithm to base 10 of the computed standing wave ratio. This is the way it will be specified most of the time, because we can see that the range of S is infinite, while the gamma can never be greater than unity. Okay, it will always be greater than or less than minus unity, or less than or equal to unity when we have total reflection. The magnetic field intensity that is associated with E1 is of course given by that equation there, where we are using the direction vector cross the electric field vector, that is E1, and we will see that it's also given by that equation there. So the only difference between H1Z and E1Z is just in this expression here, where we are having a minus, the other one we had a plus. And that's why the standing wave ratios also change. And therefore, in lossless media, we can say that maxima and minima of H1Z will occur at minima and maxima of E1Z respectively. So if the medium 2 was infinite extent after, that is, we are saying that the half plane is filled by medium 1 and the other half plane is filled by medium 2. That is, from Z equal to 0 to minus infinity, we have medium 1, and from Z equal to 0 to Z equal to infinity, we have medium 2. That's why we are saying it's of infinite extent in that particular case. Then the field distributions in the Z direction will vary as shown here. That is, the transmitted wave, transmitted electric field intensity will be given by X cap ET. This should be ET, not EI. We should, or I should have put here a tau there, but I'll try to see whether I can correct that for us in the expressions, in the whatever the results that I'll give, or the slides I give again. And the magnetic field is given by that value there. So now we look at a third example now for the normal incidence at a plane dielectric interface, and say the following. So a plane wave in a lossless medium with an intrinsic impedance eta1 is incident normally on another lossless medium of intrinsic impedance eta2 through a plane boundary. Obtain expressions for the time average power densities in the both media. Remember, if you look at this, this doesn't look like an electrodynamics question at all, because there are no equations. You can't see any equations. The things now you need to do as an electrical engineer is to understand the meaning of the words that we use. The words that we use have a unique meaning. When you hear lossless media, all it means is that the conductivity of that medium is equal to 0. And all it means is that the medium does not have free charge carriers at all, okay, which would support a current when we applied an electric field, okay? So these values are things you have to note down, that once you read your question, it has been said it's lossless, so you immediately write sigma 1 is equal to 0, and the other one sigma 2 is equal to 0. And from this expression here, okay, this statement, lossless medium, it tells you that eta1 and eta2 are not complex numbers, they are real numbers, real quantities. 2, nobody has asked you to look for the electric or magnetic field here. All we are looking for is the time average power. But we know that the time average power density is given by Poynting's vector, and therefore all it means is that you are trying to look for the expression of the fields is implicit in this statement. So you are expected to first of all find the fields E1 and H1, as well as the ET and HT in the second medium, okay? So this whole thing, everything that you have learned in electrodynamics is involved in this particular expression here, or this particular example. So we note that the average Poynting's vector is going to be given by the real, half the real part of E cross H conjugate. And the medium one, I'm using the equations that we already got before, is going to be given by the real part of the electric field intensity, E1, multiply across the magnetic field intensity, H1 here. And since we had X cross Y, we know that that will be going in the direction of the positive Z. That is X cross Y is equal to X cap. And this we can therefore correct by multiplying through. Remember, I'm using complex values here. That is, gamma is a complex quantity. It may not be complex quantity, but the example itself, we will see that this one is going to be a real value rather than a complex value. But when we do this, we can always keep in mind that those things are together with us. That is, we can keep them together to see the stuff. And now what you can see is that once we multiply this out, we'll get an imaginary part, okay, in there, which will be dropped out by the operation of taking the real part. And we see that the P1 average is going to be given by the power in the incident wave less the power reflected at the interface. Because gamma multiplied by EI0 is the amplitude of ER, is equal to ER0. And therefore you can see that the modulus gamma squared, okay, the absolute gamma squared, magnitude of gamma squared, multiplied by EIO squared, divided by twice eta, 1, gives us the power in the reflected wave. So this is the value you have in there. So,
excuse me.
Yes.
A question. If you multiply the imaginary part by J, doesn't it become a real part as well?
Why is it real? How do you resolve a complex number? You usually say it's the real part plus J imaginary part, isn't it?
Yes.
So that's what we have said. The imaginary part, the IM,
Yes.
IM does not have a J anymore.
Oh.
Isn't it?
Yeah.
That's what I'm saying.
Oh, okay.
Isn't it?
Yeah.
Yeah. So that's why the whole thing is. Now, if you look at this value here, now for the medium 2, the P average, you'll do the same thing, that is ET cross HT star or conjugate, and you should get that kind of value, and you'll get something like tau squared. And since the media are lossless, we expect that the average power density in medium 1 must be equal to the average power density in medium 2. There is a 2 missing here. In other words, if we were to do 1 minus the magnitude of gamma square must be equal to the ratio of the impedances of the two media and multiply by the transmission coefficient squared. What we should note is that when this one is a complex value, of course, we should be using the modulus value just like we are using here. And I think that's what I'll do when I correct these slides. We just put the modulus thing so that we can see that this is a real value, so to speak. So that's this is the expression of the powers between the incident, reflected, and transmitted powers into the medium. Now, a normal case that would happen, especially in reality, say for example, when you're in a room, light will be passing through the window pane, which is glass or a compound of silicon oxide and so forth. And then it will go into the airspace inside the room. And therefore we see that we have three media, okay? That is, one, we have the air outside the room. Then we have a glass interface. Then an air into the a third medium now in the room itself. And therefore, in many cases in engineering, you're going to encounter not just one interface, but a multiple of them. Okay? So this will be of interest, and we need to look at how we can handle that problem. An example of such a case would be, say, for example, if you look at the solar panels. Solar panels are supposed to get light from the sunlight and convert this sunlight into electricity through a silicon diode, okay, which we are calling the cell, the PV cell. Now, you want to make sure that all the light that is falling on the solar panel goes into generating electron hole pairs in the diode, okay, or the photodiode. And therefore, you don't want to start reflecting those things out. Okay, you want to absorb most of it. So what we'll see is that in many cases, we can always coat, okay, we coat the glass at the top with a material with a different refractive index or dielectric constant with a given thickness such that the impedance of the glass or the intrinsic impedance of the glass covering of the PV cell is converted into an impedance that looks almost like that one of air. And therefore, if eta 2 is very close to eta 1, the reflection coefficient tends to go to 0. It will vanish when they are equal. This is called impedance transformation. So this is what we are saying, that we can coat glass to reflect, to suppress the reflections. 2, we can also look at, it's called a radome. A radome is an Adobe kind of installation, usually in the form of a spherical surface, where you put the radar installation or the radar equipment inside with the antenna to try and protect them from what the weather changes or the elements of weather. But therefore, then once you have introduced a boundary between the installations themselves, that is the antennas and the equipment, then your signal will be reflected at those walls that you have introduced before they arrive at the radar. And since you want all of it to come to it, then you must reduce the reflections from those and from the enclosure. Okay. So the reason is that you want it to allow propagation of the waves through the enclosure with little reflection as possible. I'm sure you have seen, say for example, if you drive in the night, it's very difficult to see especially when the Kenyan driver who likes just putting on the full light, you'll be getting all the light on you, and usually you want to reduce that glare, and therefore you can always put that glare with that kind of suppression of the coating. So a multiple plane interface structure would be shown as follows. We are putting in a medium 2 between two media, that is medium 1 and medium 3, and we separate them by a medium 2. But now this medium 2 does not have infinite, it's not of infinite extent. It has a given thickness L. Now we expect that the reflected wave or the transmitted wave from the interface at Z equal to minus L will travel, and it will meet this interface between the medium 3 and medium 2, and it will also suffer reflection here. And then part of it will be reflected, will be transmitted out. So we are saying we can represent the field components in medium 1 by as follows: as a superposition of the incident field components and reflected field components. In medium 2, we know that this, after reflection, the reflected wave will come here, get reflected, some of it will be transmitted back into the medium 1, and there will be multiple reflections. So in the steady state, all we have is that this will be a sum of the reflected waves at medium at the interface at z equal to minus L plus the transmitted, okay, the reflected waves at this point, that is media at z equal to 0, that are transmitted into it. And therefore ER and EI are not simply related as we saw before for the normal for the other case of only one interface. And therefore these two are also given, will be a complex kind of relationship with the incident wave itself. Okay, so we have represented them in the following form. So we have an E2 minus and an H2 minus, E2 plus and H2 plus. This represents the forward, the wave moving in or propagating in the positive z direction, and that represents the wave propagating in the minus z direction with medium 2. So this is what we have to do. We say that what we note is that reflections will occur at the interfaces at z equal to 0 and z equal to minus L. There is a reason why I've put the z at this point. It will simplify our analysis. You can always put z here, okay? But then we'll start dealing with things that have phase angles or phase factors, which we want to remove out of our expressions and leave them only for this end here. Okay, it's more like when you are dealing with cascaded amplifiers in electronics. I think FEE 302. You always started at the load and analyzed your amplifier towards the source. So that's the same kind of philosophy I'm using here. That is, I start from the load end where the load termination is medium 3. Then we'll have a medium 2 here. Then we'll get the values of that medium and then come to this, and we can express therefore all of this in terms of EI alone. So medium 2 is of infinite extent. Multiple reflections will occur there, and therefore we expect that the wave will consist of the contributions from the reflections. Now, suppose the incident wave is assumed to be x-polarized as shown in the diagram. Then we can write that the total field in medium 1 is going to be given by that equation there. That is E1 equal to the incident wave plus the reflected wave. And the H field is going to be given by 1 by eta 1, that is the intrinsic impedance of medium 1, by the reflected incident wave minus the reflected wave. Now, the reflected field component in medium 1 will consist of fields reflected at the plane at z equal to minus L, fields transmitted into medium 1 from medium 2, okay, after reflection at the plane at z equal to 0. The fields in medium 2 consist of the components transmitted from medium 1 across the plane and the reflected components from the plane at z equal to 0. And therefore, the medium 2 fields are going to be given by the following form. That is, we are going to give them as E2z equal to x cap, that is E2 plus, that is the wave propagating in the positive z direction, plus the wave propagating in the minus z direction, and the H2 as well will be given as given there. Okay, so our task is to express this E2 plus and E2 minus in terms of the intrinsic or the incident wave quantities, that is EI0. So in medium 3, we may assume that the medium 3 is now of infinite extent, and therefore there will be no reflected waves there because there's no other interface to the right of the interface at z equal to 0. Okay, and therefore we can see that the only fields that are there are only those transmitted through the interface. And therefore, the fields in medium 3 can be written in the form et z equal to x cap et0 exponent of minus j k3z. And ht is given by that equation there. Okay? If you look at these equations, the equations you are dealing with, you can always reflect your physical electronic and see that this is the case of where we have an electron wave going through a barrier, okay, of finite extent, okay, finite thickness, what we were calling tunneling. So the equations are just the same as the ones we did in the second year. So what we are going to do is to use the continuity or the boundary conditions required for the tangential field components at the two interfaces, okay? And this will allow us to express all the fields in terms of the fields of the incident wave. So the continuity of the component at z equal to 0 will require that E2 plus plus E2 minus must be equal to E2 0. That is the continuity of the tangential component of the electric field across the interface. And the continuity of the magnetic field across the interface will be given by that value. So we can therefore write that E2 plus is just simply 1 plus eta 2 by eta 3 and multiplied by the transmitted wave component here, ET0 divided by 2. And the E2 minus is going to be given by 1 minus eta 2 by eta 3 ET0 by that. And this you can always see that is going to be given by, we know that ET0 is just given by E2 plus multiplied by that, and we are dividing that. Okay, we have just used a division here to give us at E2 plus. And therefore we see that it has a form of a reflection coefficient, whereby we have an intrinsic, a load, okay, of medium. The medium 3 is terminating a medium 2 with characteristic impedances eta 3 and eta 2 respectively. Okay? And therefore, we can write that the reflection coefficient at z equal to 0 is given by gamma of 0 defined as E2 minus by E2 plus, and this is going to be given by eta 3 minus eta 2 over eta 3 plus eta 2. And this is an important kind of result there. Now, if we start moving from the interface at z equal to 0, okay, in the minus z direction towards the interface at z equal to minus L, we can always get values for the E field, okay, as follows. As E2 at a given point z is going to be given by E2 plus into the exponent of that minus, that is the forward moving wave, plus the reflected wave in medium 2. And the magnetic field will also be given the same way, just like before. In this case, we are just assuming the medium 1 is no longer important to us. We are just looking at a point in medium 2 and medium 3 interface, which is a single interface. And this, we can see, we recall they are the same expressions as we had for the single dielectric interface, only replacing the field amplitudes by a different quantity here. And therefore, we can always define a wave impedance or an intrinsic impedance in medium 2, okay, at a distance z from z equal to 0 in the following form, as the ratio of the electric field divided by the ratio of the electric field to the magnetic field at that point. And once we see that, we can see that it's going to be given by the eta 2 exponent of minus j k2z plus gamma 0 of that and that. So all we are going to do now is to replace the value of gamma 0 with the its definition, that is eta 3 minus eta 2 over eta 3 plus eta 2, and we get the following equations. That is, we'll get that eta 2 is going to be given, that is z, what is it called? Then after we have gotten the value of z, we can now go towards and look at z equal to minus L and look towards z equal to 0 plane, and we'll get a value of z minus L. And we can see that it's more like in the circuit theory, where you are looking toward the load or termination from the generator side. And therefore, we can call that as an input impedance looking towards the plane at z equal to 0. And we see that is going to be given by this expression, that it's eta 2 multiplying eta 3 cos k2l plus j eta 2 sin k2l over eta 2 cos k2l plus j eta 3 sin k2l, where we are replacing each z that we have in the expression for zz with minus L. And that's why we have a change of the signs of the two components of exponents. Now, this would be the input impedance that will be seen by the incident wave looking towards the interface at z equal to 0 if that medium 1 was not present, okay? That is at the plane z equal to minus L. That's what it will be seen. And therefore, we note that the medium 2 has transformed the impedance eta 3 of medium 3 into a new impedance, okay, equal to Zi as given by that expression there. I'm sure in transmission line you also divided through by the cosine and you got the tangents here, okay? It's just the same kind of equation that you already obtained in whatever transmission lines. And therefore, we can call such a structure an impedance transformer. That is, we are transforming the level of impedances of between two media, so to speak. So suppose medium 2 and medium 3 were replaced by a medium of intrinsic impedance equal to Zi, having infinite extent, then the wave propagation, okay, or the wave propagation characteristics at the Z equal to minus L plane will remain unchanged, okay? So the reflection coefficient therefore at Z equal to minus L is will be given as gamma, which we define is at the gamma at minus L is going to be given by Zi minus Z eta 1 or Zi plus Z eta 2, where we are using the expression for reflection coefficients. Now, it's the same as saying this, that medium 1 or the transmission line with the characteristic impedance eta 1 is terminated by an effective load Zi. Okay? So, example 4. So this, I think I should give you a 5-minute break, or what do you say, guys?
Yes.
Yeah, take a 5-minute break so that we can see, we can look at the example slowly. So we'll meet at 10:11 then.
Excuse me, sir.
Yes, sir.
Now that there are two waves in medium two, when we're balancing the equations with those of medium one, do we need to change the direction of the wave that was reflected from medium three? Or
Do I get it? You see, once immediately we have this, let me show that again. In that diagram. Yeah. So what I'm saying is this. Once we have all this, This now represents all those waves that were reflected, many reflections that are happening. All right? Again, this one is a superposition of the wave coming in that direction, all right? And the wave that started from here, okay?
Yeah.
So they are all added up together in there, okay?
Oh,
So
okay.
this represents an effective value.
Oh.
You don't have to start looking at the little components. They are not important anymore.
Oh, okay.
So this represents the total fields as they look there, all right?
Yeah.
Yeah.
Okay, thank you.
You're welcome. So now we can continue. I don't know where we were before. We were talking about the example 4. So a dielectric layer of thickness L and an intrinsic impedance eta 2 is placed between medium 1 and 3, having intrinsic impedances eta 1 and eta 3 respectively. So what we are required to do is to determine a value for the thickness of that medium, which we are calling medium 2, and its intrinsic impedance, assumed of infinite extent, that will ensure no reflections occur when a uniform plane wave in medium 1 impinges normally on the interface with that medium that we are dealing with. That is, if we were to look, if we were to make an interface between medium 1 and 3, we'll get reflections. But if we separate medium 3 and medium 1 with a medium 2 of thickness L, then we can see that the wave from medium 1, the incident wave in medium 1 will be transmitted totally towards the interface at medium 3, okay? And this is just by looking at what we saw as the gamma at minus L. We want the gamma at minus L to be equal to 0, which means that the Zi that we computed must be equal to the intrinsic impedance of medium 1. So we can say that we require gamma 1 to be equal to 0, where that is gamma 1 is the gamma at minus L is equal to 0. And we require that Zi be equal to eta 1. And therefore, all we need to write there is that when we get the expression for for gamma 1 or gamma minus L, in terms of Zi represented by its value using medium 2 and 3 intrinsic impedances and characteristic impedance and whatever, and the propagation constants, we should get this kind of equation where we have a real part and a real part and an imaginary part. And the only thing we need to do now is to equate the real parts together and the imaginary parts together, because two complex quantities are only equal if and only if their real parts are equal and their imaginary parts are equal as well. So we have two equations that eta 3 cos K1 L, K2L is equal to eta 2 cos K2L, and for the imaginary part that eta 2 squared, appearing from this point here, eta 2 squared must be equal to, multiplied by the sine K2L is equal to eta 1 multiplied by eta 3 and the sine of K2L. So this come from that equation there. And we shall see the conditions for which this becomes, these equations hold. We note that the condition eta 3 cos K2L equal to eta 1 cos K2L will hold if we have eta 3 equal to eta 2, okay? Or we have the cosine of K2L equal to 0, okay? If that one is equal to 0, then eta 3 and eta 1 can have any value. But if eta 3 is equal to eta 1, then the cosine cannot be 0. Okay, it can have any value. And therefore, it means that when we look at the imaginary part, okay, for cosine of K2 equal to 0, then the sine of K2 cannot be equal to 0, because we know that the cosine and the sine are orthogonal functions, okay, and they appear at the minimum, appears at the maximum of the other. Therefore, if cos K2L is equal to 0, then it means that eta 2 must be given by eta 1 multiplied by eta 3, the square root of the product. Okay? The condition eta 2 squared sine K2L equal to that will hold again for that expression there, or the sine of K2L equal to 0, which means that the cosine of K2L cannot be equal to 0. And therefore, if we have sine K2L equal to 0, then we must have that eta 3 is equal to eta 1. And therefore, the two possibilities for reflectionless situation are as follows. 1, eta 3 equal to eta 2, and sine K2L equal to 0. And then we can therefore have that K2L is equal to n pi, or in other words, the L is going to be given by n lambda by 2 by 2, because the K2L must be always an integer multiple of pi for us to have sine K2L equal to 0. So we'll have it as that, and this is called a half wave dielectric window because of that value. Remember that the lambda 2 is the wavelength of the wave in medium 2. Okay, it's not the medium, it would be different in medium 1, so to speak. And this is given by that equation there, where f is the operating frequency, and it is a narrow band kind of a device because it only operates, this only holds at a specific value of f. Okay, and which is very close to the, the bandwidth of the signal that you can have that can satisfy this is going to be very small. It should be as close to the center frequency as possible. Now, if we took eta 2 equal to that eta 1, eta 3, then it means where eta 3 and eta 1 are not equal, then the cosine is the one which should go to 0. And therefore, it means that the K2 of L must be equal to an odd multiple of pi by 2, or an odd multiple of 90 degrees. Therefore, it gives us a value of L equal to 2n plus 1 and lambda 2 by 4, where n is equal to 0, 1, 2 is an integer, so to speak. This is what is called a quarter wave impedance transformer that you found in transmission line theory. Now, we look at now the case of oblique incidence on a plane dielectric interface. And as you recall yesterday, we say that now when we have oblique incidence, then the polarization state of the wave becomes of importance. Now we'll start by looking at a normally polarized wave that is incident obliquely on a dielectric plane interface at an angle of incidence theta I measured with respect to the normal, outward normal to the interface. And they are calling it theta I and theta R there. Now remember all these cases we did, we said that we could resolve the Ni into a next component and a Z component. The Hi will be resolved into an X component and a Z component. And then we can analyze the case. Now, this is exactly the same case we did when we were looking at oblique incidence using a good conductor. The only thing that has happened is that we have put now the sigma equal to 0 rather than sigma equal to infinity. And because of that, we'll have a transmitted wave going into the medium 2 at an angle of transmission or an angle of refraction theta t. So from the geometry of the structure, the direction vectors are given as follows. That is, Ni cap is going to be given by S cap sine theta I plus Z cap cos theta I, and NR cap is given by that equation, and the NT cap is given by that. So these are the unit vectors of the direction vectors for the incident wave, the reflected wave, and the transmitted wave. And therefore, the fields in medium 1 will be, and the transmitted, the incident wave fields, the electric field given by that, and the magnetic field will be given by that value there, which comes out to that equation there. And the reflected waves with ER given by that and HR given by that. Remember, always try to get HR in these terms. You will never go wrong, because once you have fixed fixed the direction of ER, the direction of HR will be fixed by that equation there. Okay, don't try to deduce it, but just compute it that way. You'll always not go wrong. In medium 2, we of course have the transmitted waves, wave components, and then they are given by that equation there, and the magnetic field intensity given by the same kind of value. Remember, never forget that when you go to a different medium, it will have a different intrinsic impedance and a different propagation constant, K. So continuity of the tangential components of the total fields at the interface then will require that the incident wave component in the x direction, or the x component of the incident wave plus the x component of the reflected wave must be equal to the x component of the transmitted wave at the interface along in the x direction along that interface. And the magnetic field, that is the incident magnetic field component, the x component of the magnetic field, and the x component of the reflected magnetic field must be equal to the x component of the magnetic field component along the interface, that is. So for these equations to hold for all values of x along the interface, the components must have the same phase factors in the x direction. That is, the exponential factors that we have must be equal. We call this, especially when we'll be analyzing waveguides, we'll call it phase matching. It's a phase matching technique along the interface. We are matching all matching all the phases there. And therefore, all that means is that K1x sine theta I must be equal to K1x sine theta R, and it must be equal to K2x sine theta T. In other words, we can have that sine theta I is equal to sine theta R equal to K2 by K1 sine theta T. Now here we'll extract two conditions. One, that the sines are going to be equal. The sine theta I will be equal to sine theta R only if theta R and theta I are equal, and we say call this the reflection coefficient, the Snell's law of reflection. The angles, that is the sine of the angle of refraction, must be equal to K1 by K2 and multiplied by sine theta I. And if I was to replace K1 and K2 by omega root mu1 epsilon 1 over omega mu2 epsilon 2, I'll get it as shown there. That is the ratio of the magnetic field in magnetic permeabilities and the electric permittivity, and multiplied by the sine theta I rather. And this equation here, usually for non-magnetic materials, mu1 and mu2 will be equal, and we'll just be left with that. And the square root of the dielectric constant is usually called the refractive index, and therefore we are just, in the normal way you met it in physics, was that sine theta T is equal to n by n1 by n2 multiplied by sine theta I. That is the refractive index of medium 1 divided by the refractive index of medium 2 and multiplied by the sine of the incident, the angle of incident. So these are called the Snell's laws of reflection, that is theta R equal to theta I, and laws of refraction, that is sine theta T equal to that relationship. Okay, we have met this already in physics, and I suppose. So with the phase factors being equal, the amplitudes of the fields will then be related as the incident amplitude plus the reflected amplitude must be equal to the transmitted amplitude at the interface. And the difference must be given by eta 1 cos theta t over eta 2 cos theta I of et0. Okay, that's the relationship. And therefore, if we were to add these two equations, what we'll get a twice ei0 equal to 1 plus those values there multiplied by eta t0. And therefore, we can define a transmission coefficient, a coefficient of transmission for normally polarized waves, okay, wave with normal polarization, tau n as et0 by ei0, and this is going to be given by 2 eta 2 cos theta I over eta 2 cos theta I plus eta 1 cos theta t. We can divide through by cos theta I cos theta t, okay, that product, and what we get is that we'll get the top becoming twice eta 2 by cos theta t over eta 2 divided by cos theta t plus eta 1 cos theta I. If you look at this expression, it looks exactly the same as the reflection coefficient for normal incidence, okay, at the interface, but with the impedances of the media corrected by the angles of refraction and the angle of incidence as shown here. That is, this can be taken as an effective eta 1 prime for medium 1, and that can be taken as eta 2 prime for medium 2. Okay? So that's important to see here. That is, we can always use normal incidence, then we just correct the values with the cosines. If we were to do the same, that is, subtract the two equations we got, we would get an expression for the reflected wave amplitude. And this is what it will become. And we have it as 1 minus eta 1 cos theta t by eta 2 cos theta I, multiplied by the transmission coefficient or the transmission coefficient for that equation, for that value. And if we replace those values there, what we get is that eta 2 cos theta I minus eta 1 cos theta t over eta 2 cos theta I plus eta 1 cos theta t must be the value for the reflection coefficient for a wave with normal polarization. This again we can divide through by the product cos theta I cos theta t and express it in that form, and we see what we said for the transmission coefficient is the same here, that this is an effective impedance for medium 2, and that is an effective impedance for medium 1. So these equations are usually referred to as Fresnel's equation or coefficients of transmission and reflection, respectively, for normally polarized waves. And we note as before, if we added unity to the gamma n, we shall get this value of tau n. Now, if we look at the expression for gamma n, we can see that for gamma n here, we can see that there is a condition or an angle of incident theta I that will make this expression here become 0, and therefore gamma n is going to go to 0. Okay, we can always get a gamma n equal to 0, and if we have a gamma n equal to 0, then we have what we call total transmission. There will be no reflections at the interface. And this will be a function of theta I. So if we call that angle of incidence, theta I, we call it a theta B of n, then gamma n will vanish, and we therefore have that theta 2 cos theta Bn is equal to theta 1 cos theta t. We can express this in terms of the signs because we know what the signs are related, the relationship between the signs. We use the equation cos squared plus sine squared theta equal to unity. We can always change this into a sign, that into a sign. And this is what we have done here, that we have taken that 1 minus the sine squared of theta Bn equal to eta 1 root 1 minus sine squared theta t. Remember that this is related from the Snell's law of refraction. We can relate that to the angle of incidence theta Bn. So when we square this, we get that the sine squared theta t is equal to 1 minus eta 2 eta 1 all squared and into 1 minus sine squared theta Bn. And when we use the Snell's law of refraction, we get the following equations. Remember that eta 2 and eta 1 are also related to the mu and epsilon. This would be the root of mu 2 by epsilon 1, that epsilon 2, and this would be the root of mu 1 by epsilon 1. And these ones are related the same way. But for this particular case, we haven't done that. And all we have done is to get this into the subject, and we get the value for the angle of incidence that we are talking about, the special angle. So we can correct that immediately in that form, and we see that once we replace this by the values, what we get is that 1 minus mu 1 over mu 2 into epsilon 2 epsilon 1 must be given by that value, where we are using the difference, okay? We are using the difference of, what is it called? The difference of squares. We can always split it up into 1 plus the argument multiplied by 1 minus the argument at the bottom. And this will help us make a few deductions. We can see that the sine beta, the sine theta Bn is going to be given by that equation. Now, this angle that makes the reflection coefficient 0, this angle of incidence that makes the reflection coefficient equal to 0 is referred to as the Brewster angle. And it's a Brewster angle for the normally polarized wave. And it is also the incident, the angle of incidence at which no reflections will occur at the interface. We shall see that for normally polarized waves, this one does not exist. We cannot get a value of the theta B that makes this sign a real value, so to speak. And this is the following, the reason. That is, if we have two media that are non-magnetic, and therefore mu1 and mu2 are equal, what it means is that we'll get that 1 minus epsilon 2 at the top, but at the bottom, we'll get this problem where we have 1 minus mu1, mu2. They are equal, therefore this will make this equation go to infinity. But we all know that there is no single day that the sine of an angle can be infinite. And therefore this equation will not hold for non-magnetic media. It won't happen. So we can conclude for non-magnetic media, then a wave with normal polarization cannot have a Brewster angle at that interface. So we can say therefore in simple terms that most practical dielectric media, theta Bn will not exist. Suppose the opposite was to happen, that the medium was, well, magnetic, but it had the same characteristic impedance, the same electric permittivity, the two media, okay? Then in that case, we can get a value for this equation here, because that will cancel that and we'll get 1 over the square root of 1 plus mu1 and mu2. So theta Bn will exist in that particular case for non-magnetic media, but such kind of media is they are usually very rare to get in reality, so to speak. Well, we could use ferrites, maybe the ones with conductors, but it really doesn't work for that particular case. So all we can say is that for all practical purposes, let's assume for a level of understanding that the Brewster angle does not exist for normally polarized waves. Now, we look at the wave now with parallel polarization. Again, just like we did before, we are going to assume the same structure and make sigma 2 to be equal to 0 as well. Okay, for the dielectric good conductor dielectric interface. And these expressions that we got before, we are going to get them here by resolving those into x and z components, resolving EI into x and z component, and ER into z and x component, just like we did before. So from the geometry again, we can see that the situation is still the same as before. And we resolve the electric fields into the components that are parallel to the direction of propagation, that is components in the direction of propagation, and components in the normal to the direction of propagation. And therefore in medium 1, we can have that the electric field intensity, that is the incident electric field intensity, will be given by that equation there, and the magnetic field intensity will be given by the usual form that we have been talking about, and it will resolve easily to y cap. And the reflected fields are given again as shown, okay, just like before. So it's the same expressions that we had before that we had already looked at. So in medium 2, the fields are then given as that, and now our work starts, that of balancing the field components. And remember, the field components that we want to balance are the tangential field components, because we know that the tangential component of the electric field intensity is continuous across the interface, and the magnetic field component, the tangential part thereof, is continuous across the interface. And therefore, once we do this, we can see that this equation now reduces to that level, which are the same expressions that we had before. Now we are going to insert the values themselves. But I think there are some few things missing, but we'll get those when we give the expressions for ER, IX, and EIX as follows. So when we do this, we do a phase match along the interface, and for this to hold for all x, we expect that the exponent of minus jk1x sine theta I will be equal to exponent of minus jkx sine theta r, and is equal to exponent of minus jk2x sine theta t. Again, this is the phase, requiring that the phase propagation factors or the phase factors be the same for all of them, for all components involved here. In other words, we have Snell's law of reflection and Snell's law of refraction, which is the same as we had for normally polarized wave. And therefore, if we added the amplitudes, we looked at the amplitude relationship, is that the sum of the incident amplitude plus the reflected amplitude is given by the cosine of the angle of refraction by the cosine of the angle of incident, and multiplied by the amplitude of the transmitted wave. The difference is given by a simple expression, which is eta1 by eta2 and multiplied by et0. And therefore, if we added the two equations, we get the following expression, that the cosine of theta by the theta t and the cosine divided by the cosine of theta I plus eta1 over eta2 multiplied by it must be equal multiplied by et0 and be given by that value. Or in other words, we can always take out the the impedances out of the bracket, and we get eta 1 by eta 2, 1 plus eta 2 cos theta t over eta 1 cos theta I equal to Et0. In other words, we can therefore define a transmission coefficient for parallel polarization as Et0 by Ei0 as that equation there. And we see that it's just going to be eta 2 by eta 1 and multiply by that expression there. In other words, all we can do is to multiply eta 2, okay? We multiply this eta 2 by cosine of theta t and divide it by, and divide the expression by cos theta t. This is what we have done there. And therefore, what will happen is that we have that an effective impedance for medium 2 and an effective impedance for medium 1, okay? And then we can see that this is exactly the transmission coefficient at normal incidence that we got, as long as we replace the impedance, the intrinsic impedance of the media by these corrected values here. But unlike that for the normal polarization, we have another multiplying factor, which is the angle, the ratio of the cosines of the angle of incidence and the angle of transmission. So we note that we can obtain that value, tau p, can be obtained from the transmission coefficient for normal incidence if eta 1 is replaced by eta 1 cos theta I and eta 2 by eta 2 cos theta t, and correcting the result by a factor cos theta I divided by cos theta t. Again, for the reflected coefficient, we'll subtract the two equations we had before from the continuity conditions. And what we get is that we are going to get that value that is going to be the minus of eta 1 by eta 2 into that, and multiply by the transmission coefficient for parallel transmission. And once we replace these values, this is what it comes to. And we again see that this equation, once we divide this equation by, okay, by cos theta t cos theta I, we get the following equation, like eta 2 cos theta t and eta 1 cos theta I over eta 2 cos theta t plus eta 1 cos theta I will give us the values of the equation, so to speak. Okay, all we have done is to multiply that one by the minus sign to exchange it to that form. So note that gamma p will therefore be obtained from the reflection coefficient for normal incidence by replacing the impedances, corresponding impedances, by those effective impedances there. Now, if we write tau p equal to 1 plus gamma p, we'll see that there will be a multiplying factor cos theta I by cos theta t out there. And it's no longer what we were saying before, that tau is equal to 1 plus the reflection coefficient. For parallel polarization, there is a correcting factor which by the cosine of the angles. Now, if we look at the expression for gamma p, we'll see that the gamma p can go to 0 when eta 2 cos theta t is equal to eta 1 cos theta I. Or in other words, that equation is correct when we apply the Snell's law. So using Snell's law of refraction, we then obtain that that equation will hold, and when we make the what we call the simplification, we can get that the sine squared of the Brewster angle for parallel polarization, we'll get that equation there, and we replace those ones by their values, and we see that this is what we have for that particular case. So if you recall from the normal polarization case, we had the bottom having the mu's and the top having the epsilons. Now we have the bottom having the epsilons alone down here. These values here should be taken, you should take a square root here, because this one, that, yeah, I think that is correct, the way it is. And thus, the sine of the Brewster angle is going to be given by that value. Now, what we are going to see, unlike the normal polarization case, we can have an unmagnetic medium which has mu1 equal to mu2 and equal to mu0, the permittivity of free space, and we can see that the sine of the angle, the Brewster angle, is a nice angle here, 1 over 1 plus epsilon 1 plus epsilon 2. Okay? And this, if we were to look at this equation here, we can see, we can draw a right angled triangle. Okay? If we take a right angled triangle, it's the same as saying the sine is equal to the height divided by the hypotenuse. Okay? And therefore it means if the angle of the hypotenuse is that, then it must be the sine squared plus the cosine squared. So the cosine squared must be root epsilon 1 by epsilon 2. And therefore we can always write this equation also in terms of either as the arcsine of that expression or the arctan of epsilon 2 by epsilon 1. Okay, that is sine over cosine, or in other words, since this medium is non-magnetic, that would be the refractive index for medium 2, and that would be the refractive index of medium 1, or the arctan, therefore, of the refractive indices n2 by n1, where n is defined as the square root of the dielectric constant. So, for parallel polarized waves, a Brewster angle therefore exists for any two non-magnetic media with different epsilons. An unpolarized wave may be expressed as a superposition of a parallel and normally polarized wave components. And because the values for theta bn and theta bp are different, that is the Brewster angles, if they exist, are different for parallel and normally polarized waves, then it would be possible for us to use an angle of incidence that will separate the two types of polarization from the unpolarized wave. That is, if we were to use an angle of incidence of the Brewster angle for this unpolarized wave, the reflected wave will consist mainly of the normally polarized component, while the component with parallel polarization will be transmitted totally into the next medium. So we can say that the parallel polarized component will be totally transmitted into medium 2 when incident at an angle of incidence of theta bp, or the Brewster angle for parallel polarized wave. The transmitted wave will be essentially the parallel polarized wave component, and for this reason, it's as if we have polarized an unpolarized wave just by using our interface, and therefore the Brewster angle will also be referred to as a polarizing angle. Now, when you are dealing with laser tubes, or even when you are trying to splice, say for example, the glass fiber, when you go to work for the telecom industry, the fibers, you'll need to make junctions with the fiber because the fiber cannot be infinitely long. And therefore what is done is that where they are connected together, they will be cut at a Brewster angle, so that a light wave that is going parallel to the axis of the fiber will be approaching the splice at an angle of incidence that is at the Brewster angle, and therefore there will be no reflection at where you have put the joint and it goes through. So we say that the quartz windows will be set at the Brewster angle at the ends of a laser tube, to use, and it can be used to also control the polarization of the emitted light wave. Again, for splicing fibers, the same thing will be done, that you don't cut it, you don't connect them at normal to each other, but you will split them with a sliding angle so that the axis is at the normal, at the angle of incidence, compared to the normal on the slope of the quarter of the side. Okay. Now, if we were to compare the reflection coefficients for normal and parallel polarized waves, we'll see that there is an angle, okay, that the two of them will be different, okay, except for when the incident angle of incident equal to 0, that is normal incidence. And we'll see that the reflection coefficient for the normally polarized wave will always be larger than that one for the parallel polarization. This you can see later when you look at the expressions themselves. You don't want to scroll back up. And therefore, if we have an unpolarized wave that is impinging on a plane dielectric surface, the reflected wave will always contain more power in the component that has normal polarization than that has parallel polarization. And this is used in making sunglasses, so to speak. The Polaroid sunglasses uses this to reduce sun glare at the guys who are basking in the sun at the beach, okay? Because many of the times, the light that is appearing, the sunlight that is reaching the eye, is one that is reflected from horizontal surfaces, in most cases, on the Earth's surface. And therefore, since gamma n square is greater than gamma p square, the light that will be reaching the eye will then be that with electric field, okay? The electric field will be normal to the incidence of the plane of incidence. That the electric field will be parallel to the Earth's surface. And the Polaroid glasses, therefore, will try to reduce this, okay, by polarizing the screen of the glass itself to try and filter this out. So example 5. The dielectric constant of pure water is 80. Remember, if you are given dielectric constant, this is not the permittivity. You must multiply this value by 80 by the epsilon naught to get the permittivity. Okay? So we can give this dielectric constant either in terms of the refractive index or in terms of the dielectric constant as shown here. If you are given by the refractive index, remember to get the dielectric constant, you have to square that the refractive index. So the question is, determine the Brewster angle for parallel polarization and the corresponding angle of transmission. And B, you are then given that a plane wave has perpendicular or normal polarization and is incident from air on the water surface at an angle of incidence that is equal to the Brewster angle for parallel polarized waves. So determine the reflection coefficients for this particular case. So for part A, it's much easier for us. We can just do that from an air-water interface. We have that the Brewster angle is given by the sine of that equation there, where we have epsilon 1 or epsilon r1 is of course the air, and epsilon r2 is of course that for water, and therefore we have this giving us an angle of Brewster angle of 81 degrees. And the transmission, angle of transmission, is therefore going to be given by the arc sine of this, the sine of the Brewster angle divided by the root epsilon r2. That is, this comes from the Snell's law of refraction. And once we do this, we get an angle of 6.38 degrees. This is almost grazing the surface of the interface. For part B, we know that the angle of incidence is the Brewster angle for the parallel polarized wave, and therefore the angle of incidence is just 81 degrees that we have computed in part A. And we know that the angle of transmission is going to be given by theta t equal to 6.38. We already saw before that the Snell's law of refraction and the Snell's law of reflection are the same for either polarizations. Now, we know that for the intrinsic impedance for air is almost that of free space, and therefore we say that we can always correct that to an effective impedance of eta 1 divided by the cosine of theta I, and we get a value of 2,410 ohms. And eta 2 is, of course, the free space intrinsic impedance divided by the refractive index, because we know that the speed of light in the medium 2 will be lower than the speed of light in medium 1 by an angle, by the square root of that value there. And therefore we see that this is going to be about 40.1 ohms. And therefore for the effective impedance for water is going to be given by 40.4 ohms there. Because the cosine of theta t is so small, okay, it's the angle theta t is so small that the cosine is almost the cosine of 0, and therefore it doesn't correctly impedance match. And therefore, the reflection coefficient is going to be given by the effective impedance minus the effective impedance of medium 1 over effective impedance of medium 2 plus effective impedance of medium 1. And this gives us a value of minus 0.967, almost going towards total reflection. You can also give this one as 96% if you like, 96.7%, depending on how you like giving your figures, so to speak. There will be no problem. They are just ratios. The transmission, the coefficient for that normally polarized wave is of course going to be given by twice times the effective impedance over the sum of the effective impedances at the bottom. And you see it's a very small value of 0.033. Now, suppose we were to have epsilon 1 is greater than epsilon 2. That is, we are coming from a more optically denser material to a less dense material. That is optical density, that so to speak. That the refractive index of medium 1 is greater than the refractive index of medium 2. And therefore, because from the Snell's law of refraction, we know that the sine of theta t is given by the ratios of the ratios of the refractive indices multiplying the sine of the angle of incidence. And therefore we can expect that theta t is going to be greater than theta I. Now, since sine theta t will be increasing with the angle of incidence, then when theta t becomes pi by 2 or 90 degrees, that is just the reflected or the transmitted wave is just going along the surface of at the interface. Then we say that the refracted wave will graze along the boundary, and any further increase in theta I will result in no further refracted wave. There will be no refracted wave. And now we have what we call total reflection at the interface. And since we are now saying we are inside a denser material, we can say that the light did not leave the region where we are generating it. It didn't go outside. So if it's in the room, it just stays in the room. And therefore we call this total internal reflection condition. So the angle of incidence, theta IC, that corresponds to the threshold for total internal reflection, that is theta t equal to pi by 2, is usually referred to as the critical angle of incidence. Now, if we were to set theta t equal to pi by 2 in the Snell's law of refraction, then it will obtain a value of sine theta IC equal to K2 by K1. For non-magnetic media, this would reduce to sine theta IC equal to the square root of epsilon 2 over epsilon 1, or that value is going to be given by that. If theta I was greater than theta IC, then we would expect that sine theta t will be given by the root of epsilon 1 by epsilon 2 sine theta I, and this is going to be greater than unity because epsilon 1 is greater than epsilon 2, and this will be greater than unity when we have that value there. And hence, although sine theta t would still remain real, the cosine would be imaginary because now we are subtracting a larger value from unity. And therefore, we can write the cos theta t as a value plus or minus j of root epsilon 1, epsilon 2, sine squared theta I minus 1. So we have an imaginary value there. Now, the direction unit vector, okay, nt in the medium 2 for a typical refracted wave will therefore be given by the x cap sine theta t plus z cap cos theta t. And if we replace this x cap sine theta t, we'll get it plus or minus j z cap and multiply it by that value there, where this is the cos theta t we are dealing with. And hence, both the transmitted electric and the magnetic field intensity will vary spatially as follows. They will vary as the exponent of minus jk2 nt dot r, as we saw before. And once we use the value of nt that we have obtained, we'll get it given as that equation there. And therefore, we can see that we can separate this out into a component, an exponent of minus alpha 2z, exponent of minus j beta 2 x squared into that equation, and beta 2 is equal to k2 multiplied by that sine theta I. Okay, this is an effective propagation constant and phase propagation constant, and that is an effective attenuation constant. It means that now the field that is transmitted into medium 2 will decay with distance from the interface. Okay, while propagating in the positive x direction. So the negative sign for cos theta has been chosen so that we can make alpha 2 greater than 0 to represent real values, so to speak, to show that we have attenuation rather than increase. And hence, when theta I is greater than theta IC, a non-uniform wave will be propagating along the interface in the x direction. Okay, and the amplitude of the wave will be decaying exponentially in medium 2 in the direction normal to the interface or in the z direction, while propagating in the x direction. Such a wave is usually called an evanescent wave or a surface wave. That is, if we were to make the relative permittivity of medium 1 much greater than the relative permittivity of medium 2, then alpha 2 will be so big that the wave decays quickly and is tightly bound to the interface or to the surface of medium 2. Okay? And we'll call this wave a surface wave because it does not go into the band. Okay? So such a case is what is used when you are looking at optical fibers. That is, you are trying to transmit the light inside the glass tube, while is there someone with their microphone on? So what you do is that you transmit the light inside the glass, and since the glass has a refractive index that is larger than that of free space, then you expect that the light will not leak out of your glass tube. But usually this is not the case, and therefore many cases will also try to do other techniques in reality to try and confine the wave inside the glass fiber. So I'll give this example, then we can call it a day until next week. I think now we are almost through with this particular topic. So the permittivity of water at optical frequencies is given by 1.75 multiplied by epsilon of naught. It is found that an isotropic light source at a depth d below the surface will create an illuminated circular area of a radius of 5 meters. What we are required to do is to determine what d is. Here, no one has asked you about critical angles and the likes, but we are going to use the critical angle because for angle of incidence from the source, for rays of light that are approaching the surface, the water surface, at angle of incidence less than the critical angle, will go out and you'll see the light yourself. Those ones that go at the critical angle will be reflected, okay, grazing the surface of the wave. And those ones very much above will therefore be reflected totally back. And since we see objects by reflected light, or we see the light source or a wave that is reflected off surfaces, then those ones which are reflected back into the water will not be seen, and therefore will create a dark area there. Okay, so because a point source, isotropic light source, means it transmits light equally in all directions. Okay, so the situation can be conceptualized in the following form. We have the point source here. We have rays of light going all the way, and these ones are approaching that angle there at the critical angle. That is the angle of incidence will be that value there. And it will be theta IC. And that will reflect that way. And this other one will reflect that way. So this one we won't see. And the only circle of light we'll see is that one. So we've been given the depth of the source and the radius of the illuminated spot on the water surface. So the only thing now you need to do is, first of all, compute theta IC, okay? And then you can use the tangent of that angle to get the value of theta of d that we are looking for. So for water-air interface, we have that theta, epsilon 1 is of course that one of water, and epsilon 2 is that of air. So theta IC is going to be given by the arc sine of 1 over epsilon r1. And we see an angle of about 49.2 degrees. And therefore D is going to be given by that angle, that is this angle OP, okay, divided by the tangent of the angle. And we get a value. I think that one is wrong. It's not OP we are dealing with, is the radius rather than the angle. This one is an error. I'll have to correct that. It's not OP. So it will going to be 5, the radius, divided by the tangent, because the tangent is going to be given by D over the 5 meters, the radius. So it's going to give us a value of 4.32 meters. So the source is at 4.32 meters. This is what would be done, especially for those guys the fishermen, who use radio waves to try and locate a school of fish. So all you have to do, you just send in a wave down, and then it will be reflected, and you can tell what distance the school of fish is as well. Submarines would also do the same, okay, to illuminate an area with an electromagnetic field, so to speak. Anything within that will be seen, and the one out will not. So I don't know whether we can do this, or I can leave you guys to deal with this. Let me see how much time we have. I don't have time. So with that, now I'm open to any questions that you may have for now, but I think we have already overstayed in class. So if you have an issue, just raise it up so that we can I can note it, and then we can discuss it next time we meet. Any issues? Are we together or what is happening?
No issues, no issues.
Okay, fine. So if there are no issues, then I'll ask you guys, as before, just go through the material. If you get any typographical errors or things that are not very clear, please raise them up. There's one guy who has been doing that, helping me a lot. I would request that all of us do the same so that we can make the class notes as accurate as possible and also to be beneficial to any other person that will be reading it. Okay? So with that, I wish you a nice weekend and we meet next week then.